This video is about redox reactions. By the end of this video, you should be able to identify what is oxidized and reduced in a redox reaction, write oxidation and reduction half reactions, and balance redox reactions for mass and charge. An oxidation-reduction reaction, often called a redox reaction, is a reaction in which one or more electrons are transferred. Oxidation refers to the loss of electrons, and reduction refers to the gain of electrons. In all redox reactions, something will lose electrons and be oxidized, and something will gain electrons and be reduced. You can't have one without the other. A handy mnemonic to help you remember which is loss and which is gain is oil-rig. Oxidation is loss, oil. Reduction is gain, rig. Looking at an example, here we have elemental sodium and elemental chlorine gas combining to form NaCl. Here I've represented sodium's valence electrons with the yellow smiley face. Of course, sodium has other core electrons, but we're only interested in the valence electrons here. When sodium and chlorine combine, sodium transfers its electron to chlorine, giving sodium a positive 1 charge and chlorine a negative 1 charge. As we know, positives and negatives attract, so we end up with NaCl. Here, sodium was oxidized because it lost an electron, and chlorine was reduced because it gained an electron. Notice also that when sodium was oxidized, its charge increased from 0 to positive 1, and when chlorine was reduced, its charge decreased from 0 to negative 1. Oxidation always involves an increase in charge, and reduction always involves a decrease in charge. It's often convenient to write oxidation and reduction half reactions for an overall redox reaction, so we can look separately at the oxidation and the reduction portion. In this reaction, cesium's oxidation state has gone down, meaning it gained an electron and was reduced, and tin's oxidation state has gone up, meaning it lost, in this case, 2 electrons and was oxidized. The oxidation half reaction, then, involves just the species that was oxidized and shows the electrons as a product. Since electrons were lost, they are a product in the oxidation half reaction. Notice also that since our charge went from positive 2 to positive 4, 2 electrons must have been lost. We can verify this because the two sides must be equal in charge. Here our left side has a plus 2 charge, and our right side must also have a plus 2 charge. Therefore, we need 2 negative electrons. The reduction half reaction reads as follows. Here, the electrons are reactants since they're being gained. There's only one because, as we see, cesium goes from a positive 4 charge to a positive 3 charge. Therefore, only 1 electron was gained. You may notice here that this equation is unbalanced in that we've lost more electrons than we've gained. So we need to be able to balance redox reactions. When we balance a redox reaction, it must be balanced for both mass and charge. Previously, we've only looked at balancing for mass. With redox, we must also consider the charge. Balancing a redox reaction for charge means that the number of electrons lost must equal the number of electrons gained. There's many ways to do this, but the easiest way is using the half reaction method. That's how I'm going to show you in this video. Using the half reaction method, we write the oxidation and reduction half reactions with electrons as reactants and products. Then we can ensure that we have gained the same number of electrons that we've lost. I'm going to start by laying out a list of steps for balancing a redox reaction. It's important to follow the steps in order, or the balancing will not work. These steps are on a handout you'll be given, so there's no need to copy them down here. They also make much more sense when applied in context, so we'll look at them applied to an example next. First, we'll start by writing the oxidation and reduction half reactions separate from one another. Note that you don't need to identify which is oxidation and which is reduction at the outset. This will become obvious as you balance, based on whether or not electrons are reactants or products. Then we balance each half reaction using the series of steps outlined here, which I'll show you in a minute. And again, this is on your handout. Then, if necessary, we'll multiply one or both of the half reactions to equalize the number of electrons transferred. And finally, we'll put the half reactions back together and cancel anything that appears on both sides. And of course, as always, we want to double check that all the elements and charges are balanced. Before we look at an example, it's important to note that we use water and H+ in order to balance our half reactions in step 2 here. This isn't just a made-up idea. We can do this because most redox reactions we're going to be looking at will be occurring in acidic solution, meaning there's a supply of H+ ions and water molecules available, and they actually participate in the reaction. Let's look at an example. Step 1, we'll write the half reactions. This just involves separating the things that look alike, essentially. And again, I've labeled these as oxidation and reduction. There's no need to do that at the outset. If you want to, you can, if it's obvious, but there's no need to figure it out right at the beginning. Now we're going to balance the half reactions separately. First, we want to check and make sure that all non-hydrogen and oxygen atoms are balanced. The only one here is manganese. We have one manganese on each side, so we're okay there. This is the step that people often forget, and it can be important if you miss it. Now we want to balance our oxygens using water. We have 4 oxygens on the left, so adding 4 water molecules will balance our oxygens on the right. Now that we've balanced oxygen, we've introduced some hydrogens. 8 hydrogens can be balanced by 8 H+ on the left. Again, H+ and water molecules are available to the system since this is occurring in acidic solution. Now we want to balance for charge. In total, we have a +7 charge on the left and a +2 charge on the right. We can add 5 electrons to the left to equalize these charges at +2 on each side. This half reaction is now balanced. Repeating this process for the iron half reaction, we see that the non-oxygen and hydrogen elements are balanced with 1 iron on each side. There's no oxygen or hydrogen to balance, so we simply need to move on to charge. We had a +2 charge on the left and a +3 charge on the right, so I added 1 electron to make both sides +2. Now we want to equalize the number of electrons transferred. Here we see that 1 electron has been lost, but recall we gained 5 electrons in the other half reaction. Therefore, we need to multiply this half reaction by 5 so that we both gain and lose 5 electrons. This gives us the half reaction shown here. Now we can add the 2 half reactions back together. Notice at this point it's easy to determine which is oxidation and which is reduction. Since electrons are being gained in the first half reaction, that's our reduction half reaction, and since they're being lost in the second half reaction, that's our oxidation half reaction. Adding them together, we get this monster here. Now we can cancel anything that appears on both sides. In this case, only the electrons appear on both sides, so they can be canceled and nothing else. If you can't cancel the electrons, that means you've done something wrong. You should always gain as many as you lose, so these should always cancel out. Now you should double check yourself, make sure all of the masses and charges are balanced, and then congratulate yourself because this is a long process. Here's some examples to try on your own. Pause the video here. When you come back, I'll reveal the answers. Welcome back. Here's what you should have gotten. Notice I've shown each of the half reactions above and the final balanced redox reaction below in bold. That brings us to the end of this video. Let's review our goals. First, we learned to identify what is oxidized and what is reduced in a redox reaction, with the oxidized atom losing electrons and the reduced atom gaining electrons. Then we learned to write oxidation and reduction half reactions. And finally, we learned to balance redox reactions for mass and charge using the half reaction method.